Hi everyone. As a psychology student, I've always been interested in how the human brain relates to artificial intelligence. For this course project, I selected a computational neuroscience paper on human reinforcement learning. Let me briefly introduce the paper I selected. The authors conducted a hierarchical two-armed bandit test while recording human brain activity with fMRI. Each trial begins with the top-level blue and yellow stimulus. If the participant presses the left button, then 70% of the time the purple stimulus appears, and the remaining 30% of the time the red stimulus appears. After this transition, the participant makes a second choice and then receives a monetary reward of either 0, 10, or 25 cents. The authors proposed three human reinforcement learning algorithms: SARSA, forward, and hybrid. Let me begin with the first algorithm. SARSA is a model-free learner, which means it does not try to understand the structure of the environment. Instead, it simply updates its action values using reward prediction adders. In short, SARSA learns directly from experience. The second algorithm is the forward model, which is fully model-based. Unlike SARSA, the forward agent tries to learn the transition structure of the environment. It estimates the probabilities of moving from one state to another and updates these probabilities using state prediction adders. Once it updates its transition model, it computes the expected future reward for each action by mentally simulating possible future paths, which is a form of planning. This makes the forward agents more flexible and goal-directed. Finally, the authors combine these two systems into a hybrid agent. This model mixes the two value estimates, the model-free value from SARSA and the model-based value from the forward model. The authors reported two key findings. First, the hybrid model provided the best fit to human behavior, showing the lowest likelihood and AIC values. SARSA performed similarly but slightly worse, while the forward model showed the poorest fit. Second, fMRI results revealed that brain regions associated with both reward prediction adder and state prediction adder computations were simultaneously active during the test. This suggests that humans actually rely on a hybrid strategy that integrates both model-free and model-based learning. This brings me back to my research question. If humans use the hybrid model, does it also learn best when implemented as an artificial intelligence? To evaluate these models, I recreated the same task in Python and implemented all three agents following the learning rules described in the paper. Each agent interacted with the environment for 10,000 episodes, and I repeated this process with 10 independent runs. For every episode, I recorded the reward the agent received. Then, to make the learning curve easier to interpret, I averaged the rewards across the 10 runs and applied a 100 episode moving average, which smooths out the noise. The results closely mirrored the behavior findings in the original study. SARSA and the hybrid agents learned quickly and reached good performance early, while the forward agent learned much more slowly, taking many more episodes to reach its asymptotic performance. However, the hybrid agents did not outperform SARSA. Their learning curves were almost identical. This suggests that while humans may rely on both model-free and model-based computations for flexibility and planning, the added complexity of the hybrid model does not necessarily translate into better performance in simple environments. So more complex environments may reveal clearer benefits of hybrid strategies. In addition, these ideas can be scaled to deep reinforcement learning, like deep Q network, by developing deep SARSA, deep forward, or deep hybrid models. Alright, so that's all from my presentation. Thanks for watching.